Hello, my name is Liz. Welcome to Lab 4 Oscillations. So here are the scientific principles that we used in today's lab. We have Newton's second law, as usual, which is just change of momentum over change of time, equaling net force. And net force for today's lab will be equal to the gravitational force and to spring force. And then we also have a new concept called the energy principle, where change in E, or delta E, is equal to work. However, in our situation, there are no surroundings, so work will be equal to 0, and then therefore delta E will be equal to 0. Then we also have kinetic energy with potential energy, delta U for both gravitational force and spring force. MGH is mass times gravity times height, which is change in Y. And then we have 1/2 K, which is the spring force constant, times S squared, which is, S is basically what represents how stretched or relaxed the spring is. And then we're also given spring data. So we have the spring force constant equaling to 6.83. The mass is equal to 0.402 kilograms, and L naught is equal to 0.123. Also the lab, we will analyze a video of a mass at the end of a spring moving in circular motions using tracker and extract its position data. Then we will construct a computational model using GlowScript. Then we will compare the predicted motion, that GlowScript code, with the observed motion, the tracker data, and plot the energy changes that occur in the system for the predicted motion. And our last goal will be to answer the final questions. So this is what the tracker video looks like. I imported the video to tracker. I mapped the masses positions, and from that I got the start and end times. We got the X and Y position coordinates, the initial position, the initial velocity, and then we also have the oscillation period T, but that was also given along with the spring force constant and the L naught. So here are things that I updated in the GlowScript code: mass, initial position, initial velocity, like usual. The gravitational constant is the same, but I did update the spring constant. I updated the L naught value, and I got L, which is the length of the spring, L hat, which is the direction of the spring, and S, which is like how stretched out or compressed the spring is. And then we also have that kinetic energy, the potential energy, and total energy equaling 0. So all this code is in the calculation loop of the GlowScript code, where we calculated the gravitational force, calculated the spring force, and the net force. Also updated the velocity and position formulas for the mass. We included that updated spring data, and we accounted for the energy changes. So this is the resulting video that we get after running the program. As you can see, the spring is oscillating, and there are a few graphs at the bottom, which I will explain in the next slide. So on the left, in the change in energy versus time graph, you can see that the potential energy of the gravitational force and the spring force are opposite. So as one goes up, the other goes down, and so forth. And the kinetic energy just continuously oscillates, but total energy stays, it is always going to be equal to 0 because there's no work being done. Here we have position versus time graphs for both X and Y. So the model and the experimental differ, not too much, but they differ enough, and we can account those discrepancies towards maybe outside forces working on the system or human error. So what does this all mean? For your model system, is the energy principle satisfied? The answer is yes. It is satisfied because total energy is equal to 0. Total energy is that line in orange. It's constant. If it were not equal to 0, it wouldn't be constant like that, but it is. So the energy system, the energy principle is satisfied. So we were tasked to make 2 separate estimates of oscillation periods using the tracker data. First, the period of oscillation from the X position data, and second, the period of oscillation from the Y position data, and then you compare the 2 estimates. So using that data up there, I concluded that the average oscillation period, X position, is equal to 1.614 seconds, and that of the Y position is equal to 1.519 seconds with a difference of 0.0595 seconds. So the difference between the oscillations has an impact on calculation of the spring force constant, spring force, and spring potential energy. And this difference could be caused by errors in the tracker analysis, and also like outside forces that we may be unaware of. So that's everything. Thank you.